Thanks a lot. Thanks very much to the organizers for inviting me to this workshop. It's my first time here at KITP, although I've been a long-time viewer of videos from the repository for a while, so first time, long time. Okay, so what I'm going to talk about today is moving a little bit away from holography and ADS. I'm going to be talking about holography in an asymptotically flat spacetime. So it's something that I don't understand quite as well in many respects as I do holography in anti-de Sitter space. But I hope that the kind of toy model that I present today will kind of be a useful step forward to help organize our thinking about some examples of holography from a more top-down perspective. And we'll focus on a construction that arises from the topological string, and in particular the topological string on twistor space, so hence all the fun I had with the title. Okay, so the motivating question is how we can work towards holography for flat spacetimes, and in particular, I'd like to think about top-down constructions, if possible, for certain holographic proposals for asymptotically flat spacetimes, in particular in 4 spacetime dimensions, which I'll focus on throughout the talk today. And I should say from the outset that I will actually be focusing on 4-dimensional Euclidean signature things, so I allied a lot of subtle issues that I have yet to understand and hopefully we'll have a better understanding of in the future. But the motivating proposal for the talk today often goes by the name of celestial holography, proposed by Strominger and developed by many, many collaborators. And I'm certainly not an expert on the literature, but let me just briefly mention that kind of the crux of the proposal is that perhaps 4-dimensional theories of quantum gravity and asymptotically flat spacetimes might be dual to some codimension 2 non-gravitational theories supported on the celestial sphere at asymptotic null infinity. And so the conjecture or proposal is that perhaps there's some extremely exotic 2-dimensional conformal field theory that encodes the physics of the 4-dimensional theory in that asymptotically flat spacetime. And this proceeds, or has at least historically proceeded, mostly from a kind of bottom-up perspective, studying asymptotic symmetries and the various interesting enhancements that they enjoy in 4 dimensions, following classic work of BMS and many other groups. Although, as we might recall, the 4-dimensional Lorentz group is isomorphic to the 2-dimensional global conformal group that acts naturally on the celestial sphere by Mobius transformations. So perhaps at the level of symmetries, you might start to hope that there's, again, a relation between some 2-dimensional conformal theory and 4-dimensional physics. And then a lot of work by too many authors for me to cite. I just cited some reviews very lazily, so my apologies for that. A lot of work proceeds in the direction of studying enhancements in various directions. And in particular, it's been fruitful from this point of view to transform to a boost eigenbasis of states rather than a momentum eigenbasis, where you can kind of naturally recast S-matrix elements as conformally covariant correlators and leverage studies of amplitudes and so on and so forth. But in particular, kind of the key motivation for the work that I want to talk about today, which came from the celestial holography community, was the following observation that was made pretty recently, maybe I think now in 2021, by Strominger, Guevara, and collaborators. And in particular, they were studying asymptotic symmetries in this boost eigenbasis, and in looking at a symmetry algebra furnished by so-called conformally soft modes, so a natural generalization of the usual energetically soft modes that govern universal deep infrared physics. And they found that, that such conformally soft modes have the structure, at least classically, of a chiral algebra. So if we think about the celestial sphere at asymptotic null infinity, and we'd like to imagine kind of a local conformal field theoretic description on the celestial sphere, if we want to think about taking an OPE limit between 2 states that are inserted at some points on the celestial sphere and bring them very, very close together, this corresponds from the 4-dimensional perspective to a collinear limit. So in some sense, and in fact, this is one of the ways that they originally derived this chiral algebra structure, by taking kind of known four-dimensional collinear physics, transforming it into a boost eigenbasis, and finding this OPE structure, or elucidating the OPE structure from that perspective. And they find very interesting chiral algebras that we're familiar with from two-dimensional conformal field theory, certain W algebras, or in the case of gauge theory, certain Katz-Moody algebras. And so, of course, a natural question that we might have after looking at their observation is, well, we understand chiral algebras in many contexts in physics, but in particular, we understand them as the symmetry algebras underlying honest two-dimensional conformal field theories. That's kind of the motivating role that chiral algebras play in our life. And here, we would, of course, really like to know, are these chiral algebras that appear as kind of classical asymptotic symmetry algebras in a particular nice basis, they're really the algebras of symmetries of a full-fledged 2D conformal field theory, the so-called celestial conformal field theory. And is that really what's going on here? And as any talk that poses a question for you right at the outset, you know, there's this rule. If I'm asking a question, well, the answer is I don't know the answer to this full question. I'll have nothing to say about a full-fledged 2D celestial conformal field theory today. All I will be able to talk about is, in more detail, the structure of two-dimensional chiral algebras supported on the celestial sphere at asymptotic null infinity for certain special theories, and I'll tell you what I'm able to make precise about two-dimensional chiral algebras only. And of course, this larger question is still very open and quite interesting to think about. So what are the precise connections that I want to tell you about that relate four-dimensional physics in asymptotically flat spacetimes to two-dimensional chiral algebras? And the key kind of statement that I want to lead with is the following. We would like to understand whether or not a 2D chiral algebraic structure on the celestial sphere is something that persists not just at the level of classical physics, which was shown by Strominger and collaborators, but also if it persists upon quantizing and taking into account loop corrections in the four-dimensional theory. Are these chiral algebras something that survive quantization or not? And one thing that we were able to show in work last year with Costello is that there's at least a sufficient condition for a well-behaved chiral algebra to persist at the quantum level, and this sufficient condition singles out only some very special theories, which you perhaps might anticipate because chiral algebras are, you know, they satisfy a lot of nice mathematical axioms that in particular focus on their locality and associativity. And if we map that back to four-dimensional physics, we're saying something about the analytic structure of scattering amplitudes. And the kind of limited pole structure that you might expect to appear in an ordinary kind of garden variety chiral algebra, when it maps back to four-dimensional physics, kind of only captures a very special subset of analytic structure. In particular, it sees kind of the poles that arise in the MHV sector, but we know that, you know, the wild world of amplitudes has quite a lot of interesting analytical behavior that might not be captured by a local chiral algebra. But there are four-dimensional theories that do have asymptotic chiral algebras that persist at the quantum level with a nice associative structure and that satisfies all the usual axioms of vertex algebras. And these are the four-dimensional theories that admit lifts to local holomorphic theories on twistor space. And this is an extremely limited and special class of theories, but nonetheless, this is the statement that I can make precise. And so firstly, well, what kind of four-dimensional theories admit such lifts? And it's been known for many years now, I won't put a date on it, but since work of Penrose going back at least to the 80s, possibly the 70s now, that if you study kind of nice self-dual theories, like the self-dual limitive gauge theory, theories of that nature, at least classically they can be reformulated as nice local theories on twistor space. So that gives us a hint of the sort of theories that encode a chiral algebra structure. But in fact, when we want to think about quantization of these four-dimensional theories or quantum corrections, the story is even a little bit more subtle, because it turns out that the local holomorphic theories on twistor space that are the lifts of, for example, self-dual gauge theories or other theories that you might be interested in, actually suffer from gauge anomalies at one loop on twistor space. Which again is perhaps not too surprising because a holomorphic theory is like a chiral theory, so we might naturally expect it to suffer from some gauge anomaly, and indeed that turns out to be the case. So what Casello and I studied in our work was that for local holomorphic theories on twistor space, not just classically but at the quantum level, in cases where we can actually cancel the gauge anomaly and repair the six-dimensional theory, we can construct a chiral algebra not just classically, but quantum mechanically as well, that is a nice, well-defined, and in particular, associative chiral algebra. So this is a very strong constraint on four-dimensional physics, on the four-dimensional theories we study, but it's sufficient for getting associativity of this collinear or celestial chiral algebra at the quantum level. So again, such a chiral algebra can control collinear singularities in these four-dimensional theories, not just classically, but quantum mechanically, if this very, very stringent condition is satisfied. And I'll talk about a theory, at least one example of a theory where you can construct the chiral algebra and talk about it. Good. So just to remind you briefly of what twistor space is, well, it's constructed as kind of a non-trivial rank 2 vector bundle over a copy of CP1 or 2-sphere. And I'll always give the CP1 holomorphic coordinate z. You should think of this CP1, this base of the twistor fibration, really as the celestial sphere at asymptotic null infinity. So twistor space, very loosely speaking, is a way to nicely geometrize kind of massless or null physics by encoding aspects of the twistor sphere directly into or encoding aspects of the celestial sphere directly into the twistor space geometry. As a real manifold, it's like R4 cross CP1. So if you're thinking about a Euclidean signature theory on R4, at every point in R4, roughly you have a 2-sphere living on top of that point, which is kind of geometrizing all of the null rays that you would shoot out of that point, the space of null rays. And so what I want to emphasize from this perspective is that failure of associativity in the celestial chiral algebra that you would construct for for the algebra of asymptotic symmetries of a four-dimensional theory is quite generic at the quantum level, although classically, as I said, nice chiral algebras in various examples were found. And this can be tied, at least in this context, to the existence of these gauge anomalies on the twistorial lifts of these four-dimensional theories when they exist. And I want to emphasize that from the four-dimensional theory that we're talking about is not inconsistent, even though it's lift to twistor space. The six-dimensional theory is inconsistent if you don't get rid of that gauge anomaly. But rather, you should think about this as an obstruction to integrability of the four-dimensional theory. So when the four-dimensional theory is integrable, you can always construct, that's sufficient to construct a nice associative algebra, a chiral algebra of asymptotic symmetries, even at the quantum level. And it enjoys associativity axioms. And when the 4D theory is not integrable, then, at least in many examples, you can think of this as an obstruction to integrability or a failure of a twistorial uplift of the four-dimensional theory. So all of these things, nice associative chiral algebras, well-defined twistorial uplifts, integrability, these are kind of all of a piece, and bouncing around between the six-dimensional, four-dimensional, and two-dimensional perspectives are just different ways to geometrize or encode this basic fact. Associative chiral algebras are guaranteed when you have integrable theories in 4 dimensions, but generically not otherwise. So what's an example of such a theory that actually admits a twistorial uplift where you can construct a well-defined chiral algebra of asymptotic symmetries at the quantum level as well? So here's my favorite example, although everything I say can also be applied to self-dual gravity or gauge theory with additional flavors. But I'll just be simple for today. I'll focus on self-dual Yang-Mills theory coupled to an additional scalar degree of freedom that has kind of a funny quartic kinetic term from the 4-dimensional perspective. So this theory, self-dual Yang-Mills coupled to this extra sector, turns out to admit a nice twistorial uplift. Classically, you might have just thought I could have been fine sticking with self-dual Yang-Mills theory on its own, but it turns out by recent work of Costello and also Costello and Lee, there are one-loop gauge anomalies for the self-dual theory on its own, so it in fact does not admit a local holomorphic uplift that survives quantization. So here are the theories just spelled out in a little bit more detail. So in 4 dimensions, as I mentioned, I have self-dual Yang-Mills theory written in a BF-type action, where B is an anti-self-dual 2 form. And it, by very old work of Ward and others, has been known to admit this uplift to a holomorphic BF-type theory on twistor space, where curly B is a 3-1 form, curly A is a 0-1 form. They're valued in my choice of Lie algebra, so far arbitrary. And on twistor space, I'll just emphasize that both curly B and curly A have non-trivial gauge invariances, which in the reduction to 4 dimensions corresponds to both the existence of both positive and negative helicity gluons in 4 dimensions, although they don't behave symmetrically. But there's some difference in terminology in what self-dual Yang-Mills theory means if you're a twistor person or not. So just to clarify that point. So as I said, the 6-dimensional holomorphic BF theory actually suffers from a one-loop gauge anomaly. This box diagram, as is standard in anomalies, is the source of the problem, and we need to cancel it somehow in order to have a well-behaved 6-dimensional theory, which again, as I emphasize, is my sufficient condition for getting a good associative chiral algebra. So of course, one thing you can do is supersymmetrize, and n equals 4 supersymmetry will cure this problem, and that goes back to work of Witten, and you can certainly take that route. I will not add extra supersymmetry here. I want to cancel the anomaly in a different way. And it turns out that there is a Green-Schwarz-like mechanism that will do the job in the non-supersymmetric setting for specific choices of gauge algebra G. So if you make one of these particular choices of gauge algebra, you can actually cancel the one-loop anomaly by tree-level exchange of an additional degree of freedom, as is standard in the Green-Schwarz mechanism. And indeed, there is a string origin of all of this that I won't quite go into right now. But this field in 4 dimensions is what I call an axion-like field that turns out to have a quartic kinetic term if you do the reduction down to twistor space. I call it an axion because it couples to the F wedge F term, but of course it's quite a non-standard axion. It has a quartic kinetic term. And such scalar fields have been studied before in 4 dimensions in the context of canceling conformal anomalies. So this is not a completely unheard of action. But I do want to stress that if we reduce down to 4 dimensions, this twistorial theory that's given by self-dual Yang-Mills coupled to this extra sector, well, it turns out it's actually a conformal field theory, but it's non-unitary. So this is, I mean, as you might guess, this is not necessarily the theory you would have liked to study. I would have liked to just study ordinary Yang-Mills and be able to say powerful things about chiral algebras and its 2D CFT dual, but, you know, alas, I'm not so powerful at the moment. Perhaps my power will grow, I don't know. But in any case, as I said, for twistorial theories, like the example on the previous slide, I can now construct an associative chiral algebra, including quantum corrections to the collinear scattering. And I can actually compute as well OPEs in principle order by order in perturbation theory. And these are indeed associative, as one can explicitly check. So what's the chiral algebra of asymptotic symmetries associated with my self-dual Yang-Mills plus axion example? There's various ways to think about it. For those of you that heard my talk at Strings over the summer, I don't want to bore you by going over all of this again, but I'll just say in brief that one way you can think about the generators of this celestial chiral algebra, which is very natural from a twistor space perspective, is to take corresponding fields in the 6-dimensional theory on twistor space and study certain on-shell background field configurations that are localized at points on the base of my twistor fibration, which again you should think of as the celestial sphere. So I'm looking at some field configurations that are really localized at points on the celestial sphere, so these should be local operators, if you like, in a putative celestial CFT. And for each such field configuration, I can construct states in the vacuum module of my chiral algebra or generators of my chiral algebra. And I do this for every 6-dimensional field that I have in the game. And so for curly A, I get a family of generators I call J, which in 4 dimensions correspond to conformally soft modes of positive helicity gluons. From curly B, I get J tilde, which are the negative helicity analog. And I also get 2 towers of generators from this axion field, 2 towers because it's 4th order. And moreover, you can show that these are in fact conformal primary states of mostly negative holomorphic weight. So you get a huge and patently non-unitary chiral algebra of asymptotic symmetries in this example. And you can also, of course, compute their OPEs. That was what I sold to you, not just classically, but also including possible deformations. You can do this in a few ways. So there's kind of a more abstract point of view of computing these things, and there's also a bottom-up point of view if you know the 4D collinear splitting functions, which for certain examples you might. But kind of the abstract approach to obtaining the OPEs really just comes from considering gauge invariance of these holomorphic generalizations of Wilson lines in my 6-dimensional twistor theory. So we have some integral over not a real 1-dimensional line, but if you like a complex line, or my CP1, my twistor sphere, and I study the holomorphic generalization of standard AJ couplings, which would be inserted as path-ordered exponentials into my path integral, just as I would study Wilson lines in the normal case. And then the OPEs for these vertex operators, here I've displayed J and J tilde, can be computed by demanding essentially just gauge invariance of this generalized holomorphic Wilson line operator. So in a normal gauge theory, when we do this exercise, we just get that in that case, the commutators, or the algebra satisfied by the J's, is just the current algebra for the gauge symmetry of our gauge group. We get the usual current algebra that we know and love, and nothing really happens. I mean, you get that result classically by studying gauge invariance of the action, and nothing happens to it. That's just that's the final answer. But in the holomorphic world, actually, when you expand the path-ordered exponential, you can get interesting quantum deformations, or just deformations of this chiral algebra. They're in general non-vanishing, and it can give you quite a large enhancement of the symmetry algebra that you don't normally see in standard contexts, which is perhaps not surprising. Holomorphic things, as a preview to later, kind of capture supersymmetric or BPS subsectors of physical things. So it's maybe not surprising if a supersymmetric subsector of some theory you're studying has a lot more symmetry than the full physical theory. That's perhaps not a surprise. But anyway, you can organize this computation with Feynman diagrams and just compute the constraints that gauge invariance imposes on you, and you get a nice set of OPEs for all of the currents in your problem. How much time do I have? 7 minutes, okay. I should have taken some of Shota's time. He had too much and I have too little. Yeah, I want to get to new stuff as well, but so I'll try to belabor the point maybe less than I've been doing so far. So anyway, you can compute operator product expansions for these current algebras. Here are some. At tree level, we recover if we kind of ignore the axion piece and we just look at the gluons, we recover precisely the asymptotic symmetry algebra for gauge theory that Strominger and others found. It's a certain big Kac-Moody algebra at level 0. But we can also go beyond, run my prescription, and get some deformations of this this chiral algebra as well. But I think it's also nice to just note that you can take a more bottom-up perspective and as I mentioned, the OPEs are related to 4D collinear singularities downstairs, which are of course known in detail for Yang-Mills and in particular for self-dual Yang-Mills. This is an old story. And so you can simply kind of take known collinear splitting amplitudes. Here's the non-vanishing one for self-dual Yang-Mills at one loop. Translate that into celestial sphere notation or into manifest kind of vertex algebra language and just compute the associator of what that contribution is and see if it vanishes or not. And if you do this for self-dual Yang-Mills theory without the axion, again with both helicities J and J tilde, you find a non-vanishing associator by incorporating these one-loop contributions. So the associativity without the axionic field breaks down when you incorporate these loop effects, but the axion field is, well, I should say that it's certainly sufficient for the restoration of associativity. Maybe it's not necessary, maybe there's some other mechanism, I don't know for sure, but you get additional corrections which correspond to these normal ordered products arising from the coupling to the axion, which perfectly restores associativity, and the coefficients end up being precisely fixed by that same anomaly canceling coefficient upstairs that restored gauge invariance of the twistorial theory as well. So here at least is my characterization of my chiral algebra at the one loop level. In view of time, I won't really go through this slide because I talked about it a bit over the summer, but you can prove more general isomorphisms between the four-dimensional theory, self-dual Yang-Mills coupled to this axion, and its two-dimensional chiral algebra of asymptotic symmetries, if you wish. And we proved that form factors in this four-dimensional theory, remember it's a CFT, so it's not obvious kind of what kind of scattering quantity I should compute, but it does have non-vanishing form factors, meaning scattering if I insert an additional local operator to make things more non-trivial. These form factors end up being isomorphic to correlation functions in the chiral algebra in 2 dimensions, and you can compute some examples explicitly, even though the isomorphism in abstract guarantees that this is going to work. And there's a 4D and 2D dictionary and some explicit examples that we computed. And so here is just the Park-Taylor formula for tree level in Yang-Mills theory that you get from this kind of thing. So that's fun. But in the last time, I want to tell you why this perspective leads, I think, to a nice top-down construction of an example of holography in an asymptotically flat space-time. And this is based on a short paper that already appeared, and we're writing a long paper with a lot of gory details that will appear hopefully quite soon. We're just writing up now. So motivated by these kinds of constructions, in particular the existence of 6D twistorial theories, and in fact, actually the topological string origins of that Green-Schwarz mechanism I was talking about earlier, we actually propose, also using techniques from twisted holography, which I've been thinking about as well, we can find not just a tree-level chiral algebra or a one-loop chiral algebra or a two-loop chiral algebra, but rather we're able to construct from a top-down point of view in the topological string a whole family of 2D chiral algebras labeled by a integer parameter n, more as usual in holography, which we propose is equivalent to a certain four-dimensional theory in an asymptotically flat space-time. And so in the remaining time, I'll tell you what these two things are more specifically and where they come from. And so I just want to emphasize that in contrast to the examples I was talking about so far with self-dual Yang-Mills or self-dual gravity, where we can characterize things classically, or if they're twistorial, for example, at the first few non-trivial loop orders, here everything is well defined at finite n. We have a totally bog standard chiral algebra, which we claim controls scattering in an interesting four-dimensional quantum field theory on a curved spacetime. And just to be clear about the checks, so far we've performed checks in the n goes to infinity limit, some various things at 2 and 3 points, and we conjecture that it holds beyond that, but you know, the explicit checks are a work in progress, and hopefully we'll have more to say about that a bit later. Okay, so what are the theories from whence this duality comes? Self-dual Yang-Mills plus the axion is not the only 4D theory with a nice twistorial uplift at the quantum level. In fact, if you think hard about the topological string on twistor space, there's what's called a type 1 topological string, which has open and closed sectors. The closed string fluctuations of this topological string on twistor space are a BCOV theory, as is familiar from thinking about the B-model topological string. And the open string sector is a holomorphic Chern-Simons theory, again, as is familiar from the topological string, and they're known to be coupled in an anomaly-free way. And if you study this topological string with its open and closed sectors on twistor space, and you reduce it down to 4 dimensions, so going from 6 dimensions and bringing it back down to 4-dimensional spacetime, you find the following kind of interesting and somewhat, again, special 4-dimensional theories. And I'm just on flat space for now, and I'll get to holography in a minute. In 4-dimensional flat spacetime, the open string sector, roughly speaking, gives you a 4-dimensional WZW model, whose target manifold is the group manifold for SO8. And the closed string sector gives you fluctuations of what we might call a Kähler-Scalar field, again with a funny quartic kinetic term, which you should think of as governing fluctuations of the Kähler potential. So here's the 4-dimensional WZW model. It's been studied by many people before. This is what we land on. The G equals SO8 in particular comes from string theory and the conditions of anomaly cancellation. Classically, you should think of this theory as a gauge-fixed formulation of self-dual Yang-Mills. So again, it's some very special integrable thing, but quantum mechanically, it's its own theory. And the closed string and gravitational sector, as I said, comes from BCOV upstairs, and it has some explicit action, which I didn't write down, but which I recently discovered is called the 4D Mabuchi functional. So that's something that it's nice. There's nothing new under the sun, I guess. We're just always rediscovering things that people knew in different contexts. But the equation of motion for this action tells you that the resulting theory downstairs is scalar flat, namely the Ricci scalar is equal to 0, but not necessarily Ricci flat. Okay, that's important. So again, we have a special integrable 4D theory, and I claim that this is the seed for a nice toy model of holography. And how this proceeds basically comes from doing what we do in twisted holography, which is just mimicking Maldaceno's original holographic derivation, but now where everything is a topological string theory. So we started, in view of time, I'll be skimpy on the details, and you can ask me after if you're interested in all the ingredients that go into this special example. But as I said, if we start with this type 1 topological string on twistor space, which again is BCOV coupled to holomorphic Chern-Simons in a particular way, or in the usual way, what we do is we add a large number, capital N, of additional D1 branes wrapping the CP1 on twistor space. So we're literally putting a bunch of D branes on the celestial sphere. And we compute the back reaction arising from these D1 branes, and then we can look either kind of at the quote-unquote boundary or open string side, which is the world volume of this large number of D1 branes in the topological string, or we can look at the bulk side, which is the result of back reacting this large number of D1 branes, again in the usual way, and looking at the gauge and plus gravitational sector that results from this back reacted theory. And at the end of the day, it turns out that where we started life in Euclidean, 4-dimensional flat Euclidean space, if we incorporate the brane back reaction, we find our WZW model plus our scalar flat gravity theory living on what's called Burns space. So it's a particular asymptotically flat manifold that just results from this back reaction computation that you just have to do. In the context of the topological string, back reaction really means a deformation of complex structures. So the D1 branes, well, in the physical string, they'll source some Ramon-Ramon flux. In the topological string, this becomes a Beltrami differential or a complex structure deformation. If that's to be integrable, then it has to satisfy a Moore-Cartan equation with this source term that parameterizes the D1 branes that you put on the celestial sphere. You can solve for this explicitly. It's actually kind of a cute, fun little exercise to do, and compute the resulting space-time, either back reacted in 60 or down in 40. In 4 dimensions, you get a famous metric, or famous to some communities anyway, called the Burns metric, which is a nice, smooth, 4-dimensional, asymptotically flat space-time that you might have seen studied in other contexts. So that's kind of the closed string side of our theory. And I should probably wrap, I'm a couple, okay, a little over. Okay, so just here are the two sides of the duality that result from doing this topological string open-closed duality exercise. the kind of quote-unquote boundary theory, or the open string side of the duality, again comes from the world volume theories of these n topological D1 branes on twistor space, and they support a very explicit chiral algebra. It's an SPN gauged beta gamma system that has some additional flavor symmetry and SO8 flavor symmetry, and the chiral algebra, as always, it's basically a free theory at infinite n, and we know everything about it, and at finite n you can work hard and compute the BRST reduction of this thing and blah, blah, blah. It's all totally systematic, and there's a lot of powerful bootstrap people in the audience that know how to compute these things even better than I do. And on the bulk side, again, we have our WZW model plus this scalar flat scalar, now on Berns space, this curved space-time geometry. I'm out of time, so let me kind of skip that. I'll just mention again that we can do explicit checks. We did some 2- and 3-point checks. First of all, you can match the scattering states in Berns space, both in the open and closed string sectors, to the single trace gauge invariant operators or generators of the chiral algebra. So you can make that map quite explicit. And then you can match, for example, the OPEs of the chiral algebra, which is basically a free theory computation by Wick contractions, to collinear scattering of this 4-dimensional theory in Berns space. The 4D theory, it's integrable in flat space, so the scattering is trivial, but on Berns space it becomes non-trivial, so there's actually something to compute there. And you can kind of compute, as you normally do in ADS CFT, Euclidean amplitudes by evaluating the appropriate terms in the on-shell action by the standard prescription. And okay, there's a perfect match, otherwise I wouldn't be wasting your time with telling you about this. So the duality works nicely. That's pretty much all the time I have for today, so let me wrap up. So this gives a concrete toy model of, if you wish, a celestial holography type correspondence, but here we have just a 2D chiral algebra supported on the celestial sphere, controlling scattering of a 4-dimensional theory on this Berns spacetime. So it's a very special example. Again, the ingredients come from a twistorial construction, which is very constrained by anomaly cancellation. The fact that it has these topological string origins allowed us to kind of run the usual holography program and recast it as an open-closed duality in the topological string. And then from there, we can use our usual holographic techniques to just compute things on both sides and check that it makes sense. Doing similar things for other twistorial theories, obviously of interest. Going beyond the planar limit, obviously of interest, we need to do it. For me, the main question is, the fact that we have these special non-unitary 4D theories in order to get a nice associative operator product in the chiral algebra, it's all connected to this integrability or the existence of a twistorial uplift. And so really, my question is, can you push this construction beyond these special examples, or are these special examples, are we stuck with them? Is there anything else we can do? And more, how do we think about holography and asymptotically flat spacetimes, ideally from a top-down perspective, beyond these very special constructions? I don't know. But thanks for your attention.
Thanks, Natalie. We have some time for discussion.
So I have a very elementary question. From the description, it sounded like Berns space was Euclidean. So what does asymptotically flat mean?
Yeah, I just mean it asymptotes, the metric asymptotes to delta mu nu plus quadratic plus 1 over r squared fall off as the coordinate. I wrote it in certain complex coordinates u, but as you take them to infinity, as you scale them up, so the metric asymptotes to delta mu nu.
So isn't the boundary in S3?
What's that?
Isn't the boundary in S3? Why is it a celestial sphere?
Yeah, so I don't really want to. Yeah, thinking about it as bulk and boundary might be a little bit misleading. I claim that there's an exact duality between this chiral algebra on a CP1 and this quantum field theory in 4-dimensional flat spacetime. But it's not really that the chiral algebra lives on it's a little bit different from ADS CFT in that I don't really have kind of the celestial sphere at the boundary anymore. It's just kind of an exact duality between chiral algebra on CP1 and this field theory on Berns space, which happens to be asymptotically flat.
And there's no gravity in this Berns space.
So in 4 dimensions, the kind of only gravity thing I have is this Kähler-Scalar, which is kind of like, it's similar to calling a Liouville theory gravity. I mean, it's diffeomorphism invariant, but the diffeomorphisms aren't gauged. So it's kind of gravity in a stupid sense. If we lift back upstairs to 6 dimensions, we have what's called the twistor space of Bern space. And there we get something at least a little bit more gravitational. We have a Kodaira-Spencer type theory that at least captures complex structure deformations. But, you know, we were most interested in 4-dimensional physics, and there, indeed, you know, the gravitational sector is Liouville-esque. It's not really a fluctuating metric.
Thanks.
So I just wanted to understand the action for the 4D ZW. So you wrote some action, but like a
yeah.
So the action contained like a partial and a partial bar, but because it's 4D theory, so like how does it act? Like what's the can you like give a bit more details about?
So it's the same action that was studied by, in this paper by Losev, Moore, Nekrasov, and Shatashvili. The basic fluctuating field is, it's like a 4D sigma model with maps into a certain target space. Here the target space is the group manifold of SO8, and in general it can couple to the Kähler potential of a 4-dimensional background. And there's a WZ term, like kind of a 5-dimensional WZ term, and it works very similarly to
I see.
the standard WZW model.
I see.
But yeah, this isn't, you know, we didn't originally write down this action. It just happens to be the same thing that was studied by these authors, and it turns out that you can obtain it from the reduction to twistor space of the holomorphic Chern-Simons theory in this topological string.
Okay, thanks.
Yeah.
So you mentioned that the non-associativity of the 2D OPEs can be understood in terms of anomalies on the twistor uplift. Is this always, like, is this a relation that is like two sides of the same coin, or are there examples where you have a non-associative OPE, but there is no anomaly interpretation?
Yeah, that's a good question. So certainly what I can say is that having a local twistorial uplift at the quantum level, which means canceling of the anomaly in particular, that's sufficient to get an associative chiral algebra. There are also, of course, theories that are like non-local on twistor space. Like if I wanted to deform self-dual Yang-Mills to honest to God Yang-Mills, then I would have some non-local things. And there I think the failure wouldn't be so much in the associativity axiom, but you would need to kind of make some kind of non-local generalization of a vertex algebra, which I wouldn't know how to deal with for a different reason. Like you would need to somehow allow, I think, more general general non-analyticities in the OPE. So I think, you know, if you have something local, then I conjecture that canceling the anomaly is kind of enough, and maybe it's a one-to-one thing. The best I can say is that it's sufficient, but then when you have things with non-local uplifts, I don't even kind of know how to define a chiral algebra in the usual sense. I just don't know what the OPE should be. So yeah, there's definitely layers of questions that one should ask here. I don't know all the answers.
Thanks. And another question, so if there is a holography for a flat space, we would think that, I guess, that there should be one for any dimension. I mean, well, 4D might be very special because of many reasons.
Yeah, could there be some ambitwister string version of everything I'm talking about? Obviously, people have, I mean, there's been work by my collaborator Atul and David Skinner and others thinking about ambitwister strings, which work in general dimensions. From a more world sheet point of view, I don't know how to connect them to this. Obviously, here, twistor space is quite special to 4D. Yeah, everything I'm saying about this example is very special in many ways, and I wish I had a more general understanding, but
thanks.
Yeah. So is that a world sheet interpretation of the A model, the closed string background that you had with this Burns metric? Is that something one can treat with world sheet techniques?
I mean, I would certainly hope so. I don't. So one thing already that I don't quite understand, and this probably I just need to do homework, is that it looks like there's a connection with the 4-dimensional n equals 2 heterotic string by Oguri and Vafa, which seems to be related to the 4D-WZW. So perhaps that's one route towards a different kind of stringy picture of this, but I don't understand the precise connection between their setup and ours fully, so I don't want to claim that I know for sure. Yeah, I mean, the short answer is I would fully expect topological string techniques to work and there to be a nice world sheet picture of this. We just haven't developed it.
I mean, one reason to ask is also that perhaps that's one way to try to derive the duality by open-close string on the world sheet.
Yeah, absolutely. It's like you would hope that there's some kind of proof that goes through maybe pure spinor techniques in this case that tile these pictures together maybe. Yeah, I'm totally sympathetic to that. I just don't have anything more precise to say about it.
So can I ask a very basic question? So you mentioned several times that this 4D theory is a bit special. Could you just summarize physically what are the special features that it has? For example, you mentioned something about the theory being integrable.
Yeah, on
so
flat
what do you
space-time,
exactly mean by that?
Yeah, on flat space-time, WZW4 with target manifold SO8 doesn't have any non-trivial scattering beyond 3 points. So in that sense, it's special. Relatedly, on the chiral algebra side, the BRST differential that I've suppressed but appears there won't square to 0 unless G equals SO8. So yeah, that's perhaps what I would. I think the easiest way to say the specialness is just the vanishing of the scattering of WZW4 when G equals SO8 on flat space-time.
So this 4-dimensional manifold, so that action, as Shota was asking, there is some dels and del bars, but it's 4 dimensions, so this probably, it's like C times C or something like that?
So this can be a general, if you have a self-dual Kähler manifold in 4D, then K is the Kähler potential for that Kähler manifold, and you can couple WZW4 more generally to whatever that manifold M is. And Bern space indeed has a Kähler form and is coupled in this way.
Because normally the physics of these very soft modes is that at loop levels we should resum them, and we have infrared divergences, and there's lots of physics there.
Yes.
So are we trying here to throw all that physics away, and that's why we can keep with something that? Why wouldn't we want to correct things at 3 level? That in physics, the physics of infrared physics is not just a 3-level physics, right?
Yeah, I agree. So this is a way to just try and make sense of a possible holographic interpretation of that physics at loop level. Just saying, so far what people have understood has been kind of a tree level thing, and I just asked the question, can you make sense of a 2D, like a kind of a manifestly 2D CFT structure at the quantum level, and under what conditions can you do so? And that's true for these integrable theories.
Yeah, if you don't mind, I have a couple basic questions as well. My apologies if these are obvious to everyone else. You focused on current algebras. At the beginning of your talk, though, when talking about the celestial holography kind of story, you were talking about, representing S-matrix elements in boost basis, and you get like local operators, vertex operators, not just the J's, but other vertex operators. And those in general have complex weights, if I remember correctly.
In this chiral algebra, the weights are integral, just mostly negative integer.
For the J's. But are there any other O's, I guess, is one of my questions. And related to that, are there, I just don't know very much about the bulk theories that you're starting from. Yeah. What kind of physical processes can take place, what kind of particles there are, et cetera, which would correspond to O's.
So I don't know how to get things of complex weight in this chiral algebra. I know this is related to studying things there's like this basis of states where things live on the principal series. Yeah, maybe Andrea can comment a bit more about that, but the complex weight generators don't arise here, but if you wish, that's because we're kind of manifestly capturing conformally soft things in 4 dimensions anyway, which have this expansion, this kind of very tame expansion in integral boost weights.
So you get the integer J's for all the integer deltas for all the J's here, because they come from the energetically soft expansion, which has integer powers of the energy, maps to integer deltas, mostly negative ones. But you can also ask of normal, like finite energy excitations, and they map to operators that have complex dimensions, which are on the principal continuous series. So that's that statement. And you can construct the basis of operators that live on the principal series. You can also construct the basis of operators that live on this discrete, in these discrete deltas, and they capture different aspects. One is finite energy excitation, the other one is zero energy or soft modes.
So these are really, physically, these are just the stock. This is a 2D.
The Ch's are, yeah.
Yeah, the conformally soft modes.
Yeah. Can I ask one question on that note? So from the 2D celestial CFT point of view, we have this canonically paired set of modes, like the semi-infinite tower of the modes that, so mostly negative integer conformal dimension modes, and then they are paired with mostly positive integer conformal dimension modes. And one of these towers is the interpretation of Goldstone modes, and the other is the canonical paired memory modes. Do you, for this other semi-infinite tower, do you have some interpretation in your sort of setup or from twistor space?
Partially, it would be good to understand them more, but we understand them on twistor space as certain defects that correspond to states of positive integral dimension. But they're quite understudied. You know, like in my first paper with Kevin, we identified just the fact that these things exist. This is the geometry that they have in twistor space. They would be interpreted as a certain class of modules for the chiral algebra, but we have not done much more with them. I mean, it's... Yeah, no, there absolutely should be. We didn't work it out, but I don't think it should be very hard to get. In fact, I think it's probably implicit in the twistor geometry, but I might want to think about that a little.
Okay, I suggest we thank Natalie again. And we have lunch outside, and we continue at 2 p.m.